Hello everyone, my name is Beichen Xu, a student from University of Florida. I'm taking the class Introduction to Hardware Securities, and I'm in the Edge group undergraduate number 1, and I'm doing project 3 for the final project. Today I'm going to present the automated design implementation and evaluation of arbiter-based PUF on FPGA using programmable delay lines. So here's the outline of my presentation. I will give a basic review of physical clonable function, as we all know as PUF and FPGA. Then I will have assumptions for our papers. Then I will give us an introduction of the background of the programmable delay lines. Then I will introduce the challenge 1 and the solution for that, an overview about the structure of automated turning with PDL. And then I will introduce us the challenge 2, then its solutions, and overview about PDL-based symmetric structure, including how to increase the arbiter accuracy and the trade-off between entropy and robustness. And then I will analyze and evaluate the experimental results. And finally, we will have a conclusion and a future work discussion. So first, a PUF utilize the inherent specific property of a physical device to define a unique mapping from a set of challenges into a set of responses. There are multiple types of PUF, like the arbiter-based PUF, ring oscillator PUF, SRAM PUF, and the butterfly PUFs. They are all great methods to prevent counterfeiting activities, but they all have their disadvantages for our experiment. So like ring oscillator PUF, it relies on only the specific and unique delay of an oscillating path on each device. And also, because of oscillating, it will consume a lot of powers. And for SRAM PUF, each FPGA SRAM cell would naturally tend to one logic state, and there are only a polynomial number of challenges with respect to the number of SRAM cells. So we will use arbiter-based PUF for our experiment, but it also has its disadvantages, but we will discuss that later. And for the device of our experiment, we will use FPGA because of its flexibility. Comparing with ASIC, it can help us to reprogram and improve our design to achieve the best result. We will use FPGA for our experiment. So because of that, our assumptions in this paper is that a well-designed and implemented PUFs will likely be used to identify the unique identity of each individual devices without any bias, delay differences, deviations. In other words, the PUF responses from same device should always be same under any circumstances. On the contrary, response from different devices should never be same under any circumstances. So here's our main characters, the programmable delay lines. It alters the signal propagation delay in a controllable fashion. There are basically 3 different mechanisms of doing so, but for FPGA, we can only incrementally alter in the length of signal propagation path. Like the picture showing over here, it's a method of doing so in 2008. First, it have 3 bounces, and through some dynamically reconfigure, we can change it to only have 1 bounces. However, changing circuit layout requires topological changes to the circuit, which in turn needs new configurations. So that's what leads us to our first challenge. Changing the switch connection points and routings requires new configurations, and doing so during the circuit operations is only possible by dynamic reconfigurability. The experiments on Vertex 2 Pro device show that any differential delays in a range of 947 picoseconds can be reached with a precision of plus or minus 18 picoseconds, which is pretty big. And by the way, for our experimental device, we use Synlex Vertex 5 FPGAs, which is in the device's range, which means we will have a precision of plus and minus 18 picoseconds for that, which is big. How can we really increase our precisions? we introduced the automated turning with programmable delay lines. Our objective is to have a low overhead and high precision PDL with picosecond resolution. So on the pictures over here is a 3-input LUT. Theoretically, the path through the lower dash path should be exact the same as the upper solid path over here. And like in other words, the path through A1, A2, A3 equals all 0 should always be same as the path through A1, A2, A3 is 1. However, through our observation, in the real world, the lower dash path is slightly longer than upper solid path, which results in a larger propagation delays. With this knowledge in mind, we introduce the delay characterization circuits shown over here. The XOR compares the sampled value with steady-state output of a circuit under test and produces 0 if they are same. Otherwise, it will produce 1. By swiping the clock frequency and monitoring the rate at which timing error happened, the cut delay can be measured with a very high accuracy and in an automated way. So as a result, the measurement suggests that the band maximum delay differences should be around 9 picoseconds on average, which is good and kind of solve the first challenge. And our second challenge is routing on FPGA is constrained by its rigid fabricate and interconnected structure. As a result, performing a completely symmetric routing is physically infeasible in most cases. However, asymmetries in routing when implementing PUFs can lead to bias in delay differences, leading to predictable responses, lack of randomness, and decreased responses entropy, which are not what we want according to our assumptions. So we introduced the PDL-based symmetric switch. So the old swamping switch is extremely difficult to equalize the nominal delay of the top and bottom path due to the routing constraints shown over here on the left. So for new structures we use 2 PDLs over here, the yellow triangles, to replace our old switches. A new switch structures that has symmetric implementation by constructionists is what we presented. Nominal delay values of A and D or B and C must be same in our design. So with this knowledge in mind, we introduced the new arbiter-based PUF structures over here with challenges blocks and turning blocks. The turning blocks insert extra delays into either the top or bottom path based on their selector inputs to cancel out the delay bias caused by the routing asymmetry. So I also need to explain one term, the turning level, as the differences in the number of ones in the top and bottom PDL selector byte in later experiment. For example, we use 64 blocks for experiment. When the turning level is set to 40, then it means that the 40 of the PDL blocks out of 64 are dedicated to turning, and only 24 bits of the inputs serve as input challenge. We also need to consider a few perspectives, like increase the arbiter accuracy and prevent it into its misstable state. Multiple evaluation of the same challenge to the PUF and running a majority vote on the output responses are our proposal. So with the knowledge over here, the reductions in alpha will lead to the increase of the number of repetition, which increase the accuracy and the reliability, shows the equations over here. And we also need to consider the robustness of the response. The fluctuations in operational conditions such as temperature and supply voltage can cause variations in device delays. When it achieves certain temperature or voltage level, the responses will change. However, the responses of those challenges that cause large delay differences are unlikely to be affected, like the picture showing B over here, by temperature or supply voltage variations. And on the pictures here, it shows the differentiations between the stabilities and the entrophies. It is clear to see that the responses to challenges that fall into the center partitions exhibit lower robustness compared to those in corner partitions. This is clear over here, and we can conclude that the responses from more robust challenges bear lower entropy. Okay, and then it leads us to my experimental evaluations. Here's a setup of our measurement. And first, we need to investigate the maximum achievable resolution of the PDL. Our measurement circuits here are 4 PDLs, each implemented by a single 6-input LUT, and the clock frequency is swiped linearly from 8 MHz to 20 MHz. And the results are shown on the right. The delay values in B are on average about 10 picoseconds larger than the corresponding pico values in A. And the second one, we use the programmable delay lines to implement the arbiter-based PUF on FPGA. The implementation PUF has 16 rows, each consists 64 stages of PDLs, and each PDL is implemented by 2 LUTs, each acting as inverters. So except for the routing at the beginning and the end of the PUF, the rest follows a completely symmetric pattern, which solve our second challenge. So in order to see any changes in responses, it must be turned to remove the delay bias resulting from routing asymmetry, like the picture showing over here. It basically swiping the turning level from -10 to 40, and look at the percentage of ones and zeros in each response set across different turning levels and find the set that are properly balanced. And by the way, here is the only one FPGA data result. And it is clear to see over here, if the turning level is around 20, it will get us the best result. And we also have an experiment to help improve the precision of the arbiter and test our majority voting technique. And lower transition slope in picoseconds, it will lead to higher number of repetitions, which will lead us to be more precise. Here's the experimental result about the robustness of the response. Our objective is to test the effect of robust challenge classification on PUF error rate. Each challenge to the arbiter PUF creates a delay differences at the input of the arbiter. And we can see over here the challenges in binds that are closer to the decision borders, which means smaller delta, will produce responses with larger error rates, which means smaller robustness. And because we have a trade-off between robustness and entropy, here's our entropy of the responses diagram. As we all know, the entropy is maximum if the average normalized inter-chip Hamming distance is about 0.5. And corresponding to our inter-chip Hamming distance diagram, when the partition number is around 10, it will give us the higher entropy, but it also means the lowest robustness. So here it is, and it leads to us to give our conclusion future works. In conclusion, we have automated implementations. We designed and implemented an arbiter-based PUF structure, which is novel, precise, reliable, and with robust response, and also ensure the randomness. We also consider multiple perspectives of experimental evaluations, like the method to classify challenges into different robustness groups, and the correlation between effect of power supply and temperature variations on PUF responses. So for the future work, I guess the next step is to determine how to balance entropy with robustness. This paper only qualified its existence. It didn't say how can we achieve the best result with this property, I guess. So, all right, so here's my presentation. Thank you for watching, and have a good day.